And we're kicking things off with Bill's talk on what makes Polkadot different. I want to just give a brief introduction to Bill. For those of you who don't know Bill, Bill is the author of a near-future sci-fi techno thriller. So make sure that you talk to him about that after this talk if you're interested about this book that he's written. He's also the ex-lecturer of a comp sci. I believe Bill used to be a lecturer teaching computer science at a university. Talk to him about that too. And he is basically oversees education at the Web3 Foundation. So without further ado, thank you so much, Bill, for being here today, and I'll let you kick it off.
Yeah, thank you very much. Yeah, so that's me in a nutshell. Academic who entered the crypto space and have been working at Web3 Foundation in Polkadot since 2019. So today we're going to discuss what makes Polkadot different. And there's really going to be 3 parts to this. I wasn't sure who all was going to be here and what their background was going to be. So we're going to start with a shallow swim, then have a bit of a deep dive, and then a deeper dive. So let's start with the shallow swim. This is going to be a brief overview of Polkadot. So I see some familiar faces. I know some people here are familiar. Who here has done any development on Polkadot? Like if I talk about Substrate or Rust, you're like, yeah, I know what that is. Okay, excellent. So this is going to be a very brief overview. That part might be a little bit boring if you've already been diving into Substrate, but I want to make sure that we start with the shallow swim before heading down into the deeper waters. So Polkadot is, as the lecture of, the title of my next lecture this afternoon will be, it's more than a blockchain. It is actually right now 51 blockchains. More are being added all of the time. We have a relay chain, which is essentially like the connecting chain for all of these other chains, and it provides security as well as currently some interoperability between the chains. And third parties or whoever really wants to can develop using Substrate or the Polkadot SDK to make these blockchains connect to the relay chain. These blockchains are called parachains. Connect to the relay chain, share in the security, interact with other parachains, etc. One of the really cool things that makes Polkadot different from pretty much any other blockchain ecosystem out there, with a sort of exception in Tezos, which has a similar architecture. The runtime, the rules for the blockchain are actually stored on the blockchain, which seems kind of, all right, that doesn't seem like a big difference. If the rules for the blockchain are stored on the node, like the node software, or the rules for the blockchain are stored on the blockchain, what's the difference? The big difference is the ability to upgrade more easily. So the classical way for a blockchain to upgrade is a fork. At one point you say, hey, we've got new consensus rules. Everybody out there get new version of the node software, and now we can follow, and this is a really cool chain, and just ignore this one. But this has a couple of problems. A very big problem with it, of course, is that people can still follow this chain if they don't upgrade, or if they don't agree with you, right? There have been a lot of forks, Bitcoin Cash, Ethereum Classic, that we were really trying to avoid. We wanted to have one specific chain that has economic security and that everybody could agree upon that this is the canonical chain. So by having the information for the blockchain, the runtime for the blockchain stored on the blockchain, sort of like an Ouroboros, a snake eating its own tail, we actually can update this very easily, because any chain that is following the rules of the chain, any node that's following the rules of the chain will automatically upgrade once that point occurs. So we don't need a fork. It's much easier to upgrade. If you look at Bitcoin, and they generally, they only do really soft forks, or Ethereum with its hard forks. They happen, very rarely, or even Monero, and any chain you can think of. Upgrades tend to be a difficult process. Polkadot, you can very easily do it, and so I actually ran some statistics. These are up to date as of about 24 hours ago. The relay chain since Polkadot was launched in May of 2020, there have been 52 runtime upgrades on the relay chain, 996 for the parachains altogether. Never been a problem this whole time with the upgrade process. Okay. Another great thing is that interchain communication trustless interchain communication is built in to Polkadot. So again, these statistics are up to date as of about 24 hours ago. So using XCM, chains can trustlessly interact with each other. Right now, we use something called HRMP, VMP, and DMP, which we can discuss in detail if you're interested, just different ways to communicate. But Polkadot is sending an average of a little over 2,000 XCM messages per week right now, and a total of 641,000 altogether. Polkadot has, and this is something I think really makes Polkadot different, the most decentralized and powerful governance system out there. Because all of the rules on the chain are rules for the chain are on the chain. Anything can be changed. So all the way down to the rules of the runtime, right? And the only way to do this is with the consensus of the dot holders, right? So there is no multi-sig controlling what the code is or the parameters on the relay chain. There is no, developers can do whatever they want to do. And in fact, there have been some instances where Parity, the lead developers, have proposed a runtime upgrade, and then the community has said no. So this happened on Kusama. But it's something that could happen at any time. If the developers are trying to do something that is kind of bad, then the dot holders can vote against it. And this is automatically enacted. A lot of other governance systems are really vote-taking systems, right? You can say, hey, developers, I want you to do this. On Polkadot, you vote for something and it is autonomously, I can never say this word, autonomously enacted. I can spell it though, so I've got that going for me. So this is really cool, right? That if you want to do something, if you want to change a parameter and a majority of the dot holders approve of it, then it happens. There is no way for someone to stop it. Okay. And with OpenGov, which first went live about 9-10 months ago on Polkadot, one dot is one vote. There used to be something called first-class citizens on Polkadot, so there were some accounts that had a little more power. Now, all of these accounts were voted in, right? So it wasn't like tyranny, but like the technical committee and the Polkadot Council, they had some additional minor powers. That's all gone. Now, one dot is one vote all the time. Something that I think is also very different from other chains is that the Polkadot Technical Fellowship, some of the main people that are developing the system, that is also on chain, right? It's not stored on GitHub. It's not because they're employees of some company. There are people from all over the world, from lots of different companies, and they are actually getting paid by the treasury itself. So once again, that sort of snake eating its own tail, the treasury on Polkadot is funded by Polkadot as a portion essentially of inflation, and that is autonomously swapped for USDT, and the developers actually can get paid that way. So it's a very, very cool system, and we really worked on making things as as decentralized as possible. And again, I don't know if there are other ecosystems out there doing this. I'd like to hear about it. I don't know. I couldn't find any, but I don't know every blockchain ecosystem out there. Another thing that makes Polkadot different is Kusama, our canary network. So Kusama is a network that we put the code on first that has real economic value, right? So it's not a test net. It is a canary network. And it allows us to experiment and try things out, put new code. So there's a feature coming called asynchronous backing, which is going to increase throughput and speed on parachains. And this is coming to Kusama first. We'll see if things work. Make sure that there are no issues. Similar, like Beefy the Beefy protocol, something else. It goes to Kusama first, and only if we make sure it works in a real, economically valid environment do we move things to Polkadot. So instead of just, all right, hey, things worked on the test net, I'm sure it'll work on mainnet, we have this sort of intermediate stage of Kusama. Kusama also has some other cool things. It is a very, very nerdy chain, you can imagine, because we expect things to break, but we want to try the newest, coolest stuff. There's some interesting things on it, like KSM Society, Kappa Sigma Mu, where you can get proof of ink to become part of this fraternity online. And then you can be one of 163 members so far that have gotten a Kusama tattoo, including me. I have proof of ink and it is registered on chain, and it is a human blockchain, so I'm linking back to the last person who got the tattoo. All right, so that's Polkadot in a nutshell. Again, if there's anything here people want to dig into, then we can discuss at the end, or please, feel free to come talk to me. I'm going to be here until the 4th, which I think is Monday. So please, if you ever see me, just come up and talk to me or talk after this. Happy to dive in. But let's dive into some specific differences between some other chains that Polkadot is often compared to. So, obviously there are more chains than just these, but again, I've been involved in Polkadot a long time, and these are like the 3 that I would say people ask me about the most. Like, how is Polkadot different than this? Or I heard Polkadot is just Cosmos but pink, or something like that. So one of the big differences, like the sort of philosophical difference between Polkadot and Cosmos, is the idea of a central chain and shared consensus, or more sovereignty in the chains. So obviously, I think it's pretty obvious, everything here. I'm very much a Polkadot zealot. I really like Polkadot, but I'm going to be, we're all, I think, hopefully, relatively technical here. I'm not here to shill, so I'm not going to Polkadot is great because it does this. I want to talk about this, objectively. These are 2 different philosophies, right? But I do think it makes a big difference in how, if you're deciding to build on one chain or another, what you want. So the big benefit for Polkadot, as I mentioned, I had that little diagram a while back. I think I overloaded this. Right? I just can't go that fast. Okay. This diagram. When you're part of Polkadot, right, you are signing up, right, to be a part of Polkadot, and you can leave at some point, right? You're developing this in Substrate. You can decide I want to go my own way, but to be a part of Polkadot, you essentially, when you join, you say, here are my rules that I'm going to follow, my runtime, and you give those to the validators on the Polkadot relay chain, and your ability to decide you're going to do something different than the rules you set out for is essentially curtailed at that point. Now, you can put rules in on how you're going to change your rules, and you should do that. But in terms of sovereignty, right, you're not entirely sovereign, right? If you want to be a part of Polkadot, you need to follow the rules, although these are rules you agreed to and wrote the code for when you first joined. Whereas Cosmos, the philosophy here is much more, luckily, I have a backup. I can use these buttons like a caveman. All right. So their philosophy, though, is that this actually provides, the downside of this is there is a weak point, right, in the relay chain, and you are giving up some sovereignty. So the idea behind Cosmos, developing a chain is secured by its own stake. So there needs to be some work done to develop, your own staking mechanism. Now, to be fair, there's a staking palette in the Cosmos SDK. It's pretty easy to add that in. But if you want to, you need to still develop, a group of stakers and determine how things are going to be deployed. But so the drawback to this is you need to think of your own stake. We now have stake that is fragmented, right, as opposed to entirely in one place. There's big problems with that, but the benefit, of course, is that you do have some more sovereignty over your own chain. Polkadot, the Polkadot SDK substrate, it's Rust. So I know we've already seen here some Rust talks. Cosmos SDK is in Go. So I've tried them both, actually. I'm not an expert, sadly, in either one of them. I've always meant to dive. I want to go to PBA and really dive into Substrate, but I'm sadly not an expert at either one of these. But it's actually a very similar layout. With the Cosmos SDK, they have they have libraries that you can use. They don't call them palettes. I forget what they call them off the top of my head, but it's a similar idea, just in Go. Polkadot, as we already mentioned, the runtime is encoded in WebAssembly, so you can have these forkless upgrades. You cannot do that in Cosmos. So the runtime is part of the node software. When you develop node software for your Cosmos chain, then you are including that. So if you do want to upgrade your chain, then you essentially have to do a fork, which means you need to interact with all the nodes running your chain. In Polkadot, staking and governance are entirely separate. Now, by default on Cosmos, and I'm speaking here like of the Cosmos, the Cosmos hub. If you want to develop your own chain, using the Cosmos SDK, you can change this. But just looking at some of them, I haven't done a thorough search of all of them. But in general, staking and governance in Polkadot, staking and governance are intertwined, whereas they are entirely separate in Polkadot. I can be running a validator and have absolutely no say in governance if I don't vote, right? Or I could have like just one dot or something acting as stake for my validator, but others are nominating me, and I don't. They're nominating me, but I have no control over how they vote in governance. In Cosmos, actually, by default, if their equivalent of a nominator a delegator does not vote, then instead their validator votes on their behalf. Like that stake counts for that, which actually is interesting. I'm honestly, me as a I don't know, you're very independent. You can probably tell from my accent I'm American. So yeehaw, independence, right? I don't want anyone voting on my behalf. We kicked out the British to make sure we wouldn't do that. But there are some benefits, right? Because anyone looking at Polkadot voter turnout numbers often are very low. They're higher in Cosmos because validators get this stake automatically. So I don't know what the right answer is. I personally like the fact that the people I'm nominating, those validators are just doing what I'm asking to do, producing blocks and not getting my governance votes. But there's a different philosophy there. So another thing I think is actually quite interesting is that when voting on consensus, with Grandpa or Babe, one validator is one validator, right? And so if I have a validator with a million, with 20 million dot allocated to me, and you have a validator that somehow got into the active set with 500 dot, they're the same from a consensus perspective. Okay? Whereas with Cosmos, it's stake-based voting. So I would have, 20 million divided by 500 times as much voting power in terms of the consensus. Like, to come back online whenever there's voting, 2/3 vote for finalization. It's not based on the number of validators. It's based on the it's based on the amount of stake, which I also think was kind of interesting. Again, there are some benefits to this. There's some benefits to this. I think one of the big benefits of this is actually between this and something called Fragment and FragMMS and the various staking allocation algorithms that can be used. Actually, there's all kinds that can be used in Polkadot. You get a very focused, a very similar distribution of stake. And it turns out having a good distribution of stake across validators has a lot of benefits in terms of security, because then it's harder to get into the active set and produce blocks with a lot less than the average amount of stake. Polkadot uses nominated proof of stake. They use bonded proof of stake, which is similar, same basic idea. We've got validators, we've got delegators over there, but there are actually some protections in place so that if your validator that you are delegating to does something bad, your slash actually is not going to be as bad, right? In Polkadot, there's no real differentiation between the nominator stake and the validator stake, and there is in Cosmos. Finally, Polkadot has hybrid consensus, whereas Cosmos, at least by the default, I actually don't know if you can change it using the Cosmos SDK. But by default, the ones that all the ones that I looked at a couple of different ones, including the Atom, the Cosmos Hub, uses Tendermint. So Tendermint is sort of a classic BFT where, if you think of the CAP theorem, consistency, availability, partition, they want to have that C. They want to have consistency, right? So if they can't produce more blocks, they don't produce anymore. If there's a big network partition and like 50% of the validators or 50% of the stake go offline, then it just stalls. Right. And then some actual manual effort is required to restart the chain. Whereas with Polkadot we have this hybrid consensus. So the downside to this, again, I'm trying to be as objective here as possible. The downside is this is much more complicated, right? Tendermint, classic BFT, it's a relatively simple thing to understand. There are many more edge cases with Babe and Grandpa, the hybrid consensus mechanism, in Polkadot. So with Babe, the idea is we're always producing blocks. There are some canonical rules, but we got the A part of the CAP theorem here, right? There's always gonna be something available, but you're never 100% certain you're right on the right chain. Actually, if you look like a Polkadot.js, there's there's a Network Explorer or fork, I forget what it's called, fork viewer or something. You can see there are occasional forks on Babe even now. But they tend not to last very long. So with Grandpa, we have a finality gadget that's generally 2 or 3 blocks behind, that is 12 to 18 seconds behind, that is finalizing in a sort of Tenderminty way. Not exactly the same, but similar concept of getting the 2/3 vote. So the benefit here, right, is that if we do have a big network failure, right? So we have some huge partition and half the validators go offline. We can't reach the 2/3 consensus for Grandpa to finalize. We know it, right? Everyone knowing, well, look, hey, we're on Babe, we're not finalizing blocks here, but we can still be alive and sort of have this probabilistic finality, right? It's not provable finality, but we sort of fall back. So I always like to joke, like in a worst case scenario, Polkadot becomes Bitcoin. Worst case scenario is like, well, we know we're not 100% sure that we're on the right chain, canonical chain, but we do have that. And then when enough validators come back online, then we can very quickly hop forward rather, to finalize a lot of blocks very, very quickly. All right, Avalanche. So we already mentioned, Polkadot has shared security for parachains through the relay chain. I actually find Avalanche very, very interesting, digging into it. And so someone I know joked that it's a professor coin. And so I was like, okay, I kind of see that because there's a lot of different cool stuff happening and interesting stuff, but it does make it a little bit hard to understand at first. So Polkadot, I think, we have this nice little diagram, right, of all right, we got a circle in the middle and we got parachains connecting to it. Avalanche is sort of, central chain, for lack of a better word, central setup is tripartite. There's the P chain, which actually sort of does all the work for setting up validators and assuming, or setting up or who's going to be in their equivalent of the active set, et cetera. The X chain that actually does the transactions for that, and the C chain, which is for smart contracts, which tend to be EVM based. The C chain that's included is an EVM. There's also the capability to make these subnets using the Avalanche CLI. So basically their SDK. And it's actually kind of interesting. The subnets are in fact subnets, right? They're a subset of the validators on that are set by the P chain that are also working with the X chain you can have your own chain. So you still can make your own app chain, but you just choose a subset of the validators on Avalanche that will actually do your block production, et cetera. So these things, so I looked at this a little bit. So, unlike parachains with Substrate, which you can essentially do whatever you want, right? WebAssembly is Turing complete. These subnets default to EVM. There are ways to update this. You want to add your own precompiles. You don't need to have the exact same thing, but it's very much focused on EVM. I haven't seen, maybe there is one out there that is not EVM, but it seems like it's very much, it's sort of pushing you towards EVM for running these subnets. So just like Cosmos, forks are still required for upgrade of either the subnets or the main chains. So once again, you have Ava Labs or someone that's going to have to coordinate all of this. It can't be truly decentralized. Unlike Polkadot's governance that is entirely on-chain, Avalanche does have some minor parameters that can be tweaked, but any major upgrades need to happen via fork and are coordinated by Ava Labs. So there is some minor governance on-chain in Avalanche, but it's certainly not to the level of Polkadot. And actually, so again, being objective here, they see this as a feature, not a bug. So one of the questions that I'm always asked is, what happens if somebody puts like some garbage code up on the relay chain and 50% of the dot vote for it, right? And then you've just bricked the relay chain, and that would be very bad, right? So this is their argument against this. I have some arguments, why that would not happen. It's not, it doesn't make sense economically. And I think, people that have participated here in governance, and I know there are some people here that definitely talk a lot about governance, would note that something like this was occurring. It's also going to be very, very expensive to do. But again, this is their argument against having these, the true full on-chain governance online. So Polkadot has XCM with as a message format with XCMP and HRMP right now as actual for the actual channels. There is no trustless message passing in Avalanche between these subnets, so you have to have like a classic bridge for interacting between these subnets in Avalanche. Polkadot, we already mentioned, has slashing, where nominators and validators, like their stake is really considered to be the exact same thing. So Avalanche has a very similar system, delegated POS, but there is no slashing. Essentially, the penalty for doing something bad in Avalanche is, the validator is going to lose their stake, and that their delegators are released. So a little bit less of damage can be done from the nominator delegator perspective. So that's interesting. I always find like this idea, because Polkadot really focuses on having slashing as a core part of its security assumptions, like how things work. Well, you need slashing, right? There needs to be some penalty for doing things. So I'm always interested in Avalanche, Cardano, these like slashless staking. It seems to me like it seems very odd, but maybe I just don't understand don't understand it enough yet. Speaking of not understanding things, they have their Avalanche has their own hybrid consensus that honestly I spent some time trying to understand. It's the Snow family. It's got Snowman, Slush, Slushy, all kinds. And honestly, I looked at it for a while and I don't really understand what it's doing. However, the basic idea is it is actually very similar to Polkadot. Like it is a hybrid consensus mechanism, but it is much more complicated. There's like, we have Babe and Grandpa, they have like 5 or 6 different protocols to get to finality. And this has something to do, again, I apologize. I feel like I'm, maybe I should have just acted like, oh yeah, it's I'll just go over that. It is very complicated, but I think it is because they have these multiple chains that also need to interact with each other. And the C chain is linear. The X chain is actually a DAG, directed acyclic graph. So you have these like weird combinations of things that has a very complicated consensus mechanism. But the long run, it's rather similar to Polkadot's. All right. Ethereum, right? Everyone here probably has heard of Ethereum. This is what I get asked a lot about. So, Ethereum, unlike Polkadot, like the core idea of the relay chain is it's an L0. It's made to be shared security for parachains. Anything else that it does is something we should eventually remove. And we couldn't get rid of everything, right? Staking, identity, all of this stuff happens on the relay chain right now that probably should happen on a parachain, but it turned out it was very difficult to do. And so we're slowly doing it now. Whereas Ethereum, was always designed as a monolithic chain. Polkadot, we always knew, like, all right, the goal of the relay chain is to support parachains. So we actually look at, some of the things, these L2s that are being built on top of Ethereum, and there's you can sort of tell, I don't want to say like hacked together, but like you can tell it wasn't, yes, I'm not trying to be like insulting, but you can tell Ethereum was not originally made for this, right? I mean, they're making some changes now, right, with like proto-dank sharding and stuff to make it more suitable for this, but certainly Ethereum as it is right now, is not really meant to have these L2s. So, Polkadot SDK for developing these parachains. There are several different frameworks for building L2s on Ethereum. Runtime, once again, built into the nodes, just like, again, virtually all other blockchains out there except for Tezos, or things that are built with Substrate. There are some, actually quite a few chains out there that are Substrate-based, but not on Polkadot. But for beside, leaving those aside, Tezos and sort of the Substrate family, Polkadot and Cousins are the only ones that I know of that where you have the runtime actually in the blockchain. No on-chain governance at all. It's basically, what do the devs want to do, right? And what gets deployed, and your choice is either follow the new fork or follow the old fork, or stop using Ethereum, I guess. So Polkadot has nominated POS. Ethereum has a proof of stake that has no nominations or delegations, at least built into the protocol itself. So you need your 32 ETH if you want to be staking by yourself, or use something like Lido, right? As a sort of like third-party workaround to doing essentially nominations without running your own validator. Polkadot, no contracts on the relay chain. So actually, this is something I forgot to mention here. One of the nice things about Avalanche compared to Polkadot is you have the ability to write smart contracts, right, on their sort of your main section of chain. If you don't want to deploy to some other parachain, you actually can write smart contracts on the sort of core layer. If that's good or bad, again, it depends on what you're looking for. Ethereum, obviously, right? You've got L1 smart contracts, right? It's what it was always made for. And I think is it March 13th? The next upgrade for Ethereum is planned. You'll have this proto-dank sharding. So you'll have some other space on the Ethereum nodes that you can actually have these L2s running a little bit more efficiently. Consensus actually is quite similar. There are some differences, but also a hybrid consensus mechanism, which makes sense, right? Gavin Wood, who wrote the Polkadot paper, was CTO at Ethereum. There certainly were a lot of ideas in common, and you can see, right, that they're sort of cousins, although have developed in different ways. All right, so that's just a broad overview. When people ask me, all right, what is the difference between Polkadot and Cosmos? That's my sort of 5-minute answer, or Ethereum, whatever. So I do want to dive a little bit deeper and discuss L2s on Ethereum and how they differ from Polkadot parachains, because this is probably nowadays the most common question that I'm asked. I would say Cosmos probably 2 years ago, and I don't have statistics on this, just based on my feelings of what people have been asking me. What's the difference between a Polkadot parachain and an L2 on Ethereum? Like, they seem like they're the same thing to me. But that's because you didn't dive deep enough. So this is a very, very basic diagram of how an L2 chain is going to interact. And we'll keep diving deeper and deeper into this, don't worry. Interacts with Ethereum. So you got your main chain, like your Ethereum, your beacon chain, although you could have an L2 on some other system. And then you've got your own L2 chain, right? And you've got some nodes here that are building, and you can lock up your ETH tokens or whatever and send them here. The sequencer, there's like a smart contract here. There's going to be a smart contract or something similar up here that says, all right, I'm going to lock this on here, and then my account up here will have the capability to interact with that whatever locked ETH, or a ghost version of it up here, and the sequencer is going to let the main chain, which is going to have smart contracts that can validate what is happening on the L2. Right? So this is the basic idea. You got the sequencer here, which, as you can see from its central location on the diagram, has some centralization risk, right? Because what happens if that sequencer lies about what's happening on chain? So there are a couple of different ways around this. There's two main ways that roll-ups, two main families of roll-ups when we talk about L2s. Again, there are other kinds of L2s out there, but I would say like, optimistic and zero knowledge are the vast majority of what's out there. So the idea behind optimistic rollups is just, like my little guy there. He's very optimistic, right? He says like, I assume everything is going to work out fine. And if nobody says, right, if nobody says that this sequencer is lying to me, then let's just assume it's okay. So we'll give like people 7 days or something. And if no one issues what's called a dispute, right, that like, or a fraud report of, that the sequencer is lying, then we'll just assume it's okay. Right? So he's very optimistic. Right? Zero knowledge is, he's not. He wants proof. Right? So using zero knowledge proofs, we can include when we contact the main chain, like I can prove this is what happens. Here's my proof, right? That this is what actually happened on the L2, right? So there's pluses and minuses to both of these, right? So optimistic turns out to be very flexible, right? With zero knowledge, if you have like really complex state changes, it's difficult because there are some issues with zero knowledge proofs and like having Turing complete chains. Right? Optimistic is very easily parallelized. It's relatively cheap to compute things because assuming no one raises a dispute, no one ever says that you're doing something wrong. It's, you're just saying, hey, here's my data. That's pretty easy. If you're not doing any computing, right? That's pretty easy to compute. Or minimal computing just to interact with the other chain. Zero knowledge proofs are very computationally expensive. Okay. Optimistic, you've got a substantial amount of data compared to zero knowledge proofs. You have a lot more overhead for the same amount of transactions or same amount of data. Optimistic, though, has, there's some downsides to this too, right? So we need this challenge period whenever you're withdrawing assets. So remember I said you may have a period of, if 7 days nobody has said anything, we'll assume things are okay. So what happens if I'm the sequencer, and I try to say, oh yeah, here's, everyone on the chain said I could have all of the locked ETH, right? And I'm going to issue this to the main chain. And we can't just let that happen automatically. We need to let this challenge period go through. And so what we have is then anytime assets are withdrawn, there's this delay. Right? So those of you on Polkadot, we have our own delays too, right? Like when you want to unstake, you have to wait 28 days or 28 eras, right? So it's a lot quicker on Kusama. So similar idea, right? So that's something that's kind of a drawback compared to zero knowledge because the proof is always there and very easy to calculate and compute and make sure that people are not lying. There is no challenge period. You have essentially instantaneous finality. Optimistic, because of what we said here, right? You either require some trust in the sequencers or constant vigilance. Right? So again, my American quote, right? The price of freedom is constant vigilance. Right? So the price of using an optimistic rollup is constant vigilance. You always assume that somebody is going to be verifying someone else can verify what is happening, what the sequencer is saying is happening, or otherwise there could be consequences. Whereas zero knowledge proven trustlessly. So the way I like to think of this, and whenever I talk to the researchers on our team, I'm sure they're going to smack me for thinking this because there are differences. But at a very high level, I think of the Polkadot relay chain as kind of like the Ethereum chain. It's been custom made for implementing optimistic rollups. Right? Again, not exactly, but at a high level, this is what I think of the relay chain as, right? Because this is what are parachains? They're essentially optimistic rollups, but built into the protocol, into the parachain protocol, is this challenge period, which actually happens very quickly, which is why whenever you send a data or you send an asset from one parachain to another, it doesn't take you 7 days for it to get over, because it's built in to the protocol. Right. So if we're looking a little bit more closely at what's actually happening when you interact here, so you're some user. All right, and you are going to interact with a bridge smart contract on Ethereum, and that bridge smart contract is going to interact with the sequencer smart contract. And so these are smart contracts, right, which are not nearly as efficient, especially on Ethereum or EVM-based systems. They're not nearly as efficient as the runtime, right? You're always going to have some, whenever you're sandboxing here, you're always going to have a little bit of extra compute necessary, right? Which is why, when you look at the like high frequency traders, they're writing in C or assembly language. They want to get down to the metal as close as possible. We think of smart contracts as like programming in Python, right? There's a lot of extra work involved. Now it's a lot easier to program a smart contract than a runtime, but the down, just like it's generally easier to program in Python instead of like assembly language, but there are some drawbacks here in terms of efficiency. So generally, the user is going to interact with the bridge smart contract. The sequencer is always going to interact with sequencer smart contracts. And so let's say the user says, I'm going to lock up 10 ETH here. It's a very rich user, I guess. So it'll say, all right, I'm going to lock this 10 ETH. The bridge smart contract is going to own it. He's going to, hey, sequencer, user L1, whose address is OX whatever, is locking up 10 ETH. So the sequencer says, all right, thank you. I will interact with my own smart contract to say the equivalent user L2 account now has 10 L2 ETH. And then conversely, with an optimistic roll up here, the user is going to interact with the bridge smart contract. This should say sequencer smart contract. Sorry, copy paste there. Sequencer smart contract. So it's going to interact here and say, hey, I've got like my 10 L2 ETH that I want to exchange for my regular ETH on the main chain. So the sequencer, says it's going to happen and says that part of this is unlocking the 10 ETH, but there is this challenge period. Now anyone can be viewing this during the challenge period and submit a fraud proof. So what you need for the fraud proof, you need to say like, look, here is what happened, right? Like let's say this never took place. Okay, then I can show like, look, on the chain, right, on the blocks here, like this is what happened, and this is proof that it happened. We can see the validator signed off on this block that he says did something else than it did, and if it didn't actually happen, right, you can prove this cryptographically, right? If the validator signed off on the block, and you can check that it was in fact finalized. Then you can, generally, like, slash the sequencer or, do something else bad, right? There needs to be some penalty. You can't just allow this to happen. But at a bare minimum, it won't go through, right? You can prove during this challenge period. You can submit a fraud proof. Zero knowledge, as part of this interaction, right, we can prove without knowing what's happening on here. So like this is why data availability is important. You need to have what actually happened on the chain and have access to that L2 blockchain. But with zero knowledge proofs, you don't need that, right? So everything's instantaneous. If it came here, that means that like, yes, everything has been proven. But as we mentioned, there's a lot of extra computation involved in that, right? So anytime we have to do this, it's going to be a bit slower. Now, I'm not a zero knowledge expert by any stretch of the imagination, but there's lots and lots of improvements that have been happening all the time. Like it's a very fertile field for research, for developers, and they're making lots of improvements all the time. So maybe this will not be quite as bad. It may just be a much smaller hit in the future, but and I know, like, again, very fertile ground for research right now. But for right now, it does take quite a bit longer if you're doing anything with ZK. But the nice thing is you don't have that challenge period, right? Because the proof is built in. Right. So the interesting thing, I think, when looking at L2, and I want to, again, I'm trying to speak as objectively here as possible. So none of this is me saying something bad. This is from L2 Beat, the risks page. There's actually a lot of L2s out there that have not implemented everything necessary to have a secure, like actually be confident that you are securely interacting with the chain. So something I think is really interesting, like some of these L2s, you cannot submit fraud proofs right now. Or there's a centralized sequencer, and that is the only sequencer that's trusted, or a set of whitelisted sequencers. So if there is an issue with the sequencer or a problem, then there's no one that can jump in and just run their own sequencer or do things correct. do things correctly. So this I've always thought was like really, kind of, funny that there's quite a few optimistic rollups, and like sort of the key thing about optimistic rollups is you need to have this fraud proof, right, during the challenge period, and there's some that just don't have it, or some that actually have put it out there, have seen problems with it, and then have withdrawn it. Okay, so now in comparison with Polkadot, we talked a bit about L2s. So I think it's actually very similar, right? So on the parachain, we have collators. So collators are developing the blocks for the parachains, and then they are sending a proof of validity of this block and like what happened in that block to the validators on the relay chain. Right? And the validators already know the rules for that parachain, so they actually can run this through, make sure that it's a valid block, look at the proof of validity. And there's actually a subset of the validators that are randomly chosen and are changed all of the time, right? So it's it's a little bit different than Avalanche with subnets, where you have specific validators for your specific subnet. Here, you don't know ahead of time, or at least not more than a few minutes ahead of time, what validators are actually going to be validating your parachain, which actually is very good for security, right? This also means if we think of these as kind of like the sequencers, right? The collators are kind of like sequencers. So they're producing this. They're going to send the proof of validity along with the block that, like, yes, they sign the right. Excuse me. The right. Here is everything that has worked. We've gone through it. We can prove it. The validators actually can run through and make sure that it's not garbage. Like, they can run it themselves. They also can compile this WebAssembly and run it against the state transition that is indicated by the block that's coming in from the collators on the parachain, right? So we see here, like, it's sort of similar idea that we're doing every block, not just when there's some interaction with the relay chain. Every block, it's going through it and doing this. And when it sends this, this proof of validity and this new block, this candidate block that's coming through, there's actually something called erasure-coded chunks. Right? So what we do, remember I said whenever you want to submit a fraud proof, you need to know what happened up here. Right? You can't, there's actually all sorts of attacks that are possible if you're withholding this information. Again, this is one of the reasons like data availability is so important. So when this gets sent to the validators, and there's actually some things we won't go into to make sure that it does get sent around, it's split into lots of pieces in something called an erasure coding, excuse me. So at least 2/3 of all the validators need to have a chunk, which is a piece of this data. And any 1/3 of these chunks is necessary to reproduce the entire state transition. So we're really like spreading it out amongst all the validators. And if a bunch of these validators go offline, well, it doesn't matter as long as at least 1/3 of them exist that got this, right? Of the 2/3 that originally got them, we can recreate this in case there is a dispute, okay? In case someone does try to do things. Tries to do something bad, right? We can't always get this data and prove like, hey, this is what happened, and this is what this collator told us happened. This is kept around for 24 hours among the validators. So this is not stored on chain anywhere. The only thing that's stored on chain is the candidate receipt. So you have a bit of that stored on chain, but you don't have all of this data stored on chain. So this is Polkadot's data availability layer. Ethereum also, with proto-dank sharding, will do this in a very similar way. They keep it for much longer, though. I think 18 days. I think a big reason for that is because generally, the challenge period in Polkadot is much shorter. So you get to finalization usually within 2 or 3 blocks. So again, 12 to 18 seconds. So this is like much longer than you would need if we're actually doing something for trying to get this data after 24 hours. There's probably a big problem. Something really bad has happened. All right. So now once this comes in, enough validators have copies of the data so that we know that we're not losing it. They can all examine the proof of validity, examine the candidate block, make sure that it's correct. Right. And in the case of a dispute, we know that we're going to have the data to be able to challenge it. So all of these, this is Dolly's impression of a suspicious person, by the way. I said, give me an icon for a suspicious person. I really love DALL-E. Like, it just gives me like insight into the mind of an AI. And that is what a suspicious person looks like. All right. So they're all going to examine it, and assuming everything is okay, this is that they're going to say, all right, they're going to sign off on it and get into the blocks in the relay chain, and we're good to go. On the other hand, if we had some evil cheater coming in here, and that was Polkadot's, that was DALL-E's evil cheater icon that I put there. That's what an evil cheater looks like. And we can prove this, right? Then they actually can slash the validator that originally said, like, oh yeah, I trusted this, it was good. Again, there's other reasons for possible slashes, like if a large number of validators go offline, or if they equivocate, they produce two relay chain blocks at the same height. But the biggest one, the thing we really want to avoid, and what causes up to a 100% slash, is if a validator gets a parachain block that is invalid and says that it is valid. And all of these other validators are incentivized to be checking this. So on these L2s, and again, maybe one of these, I'm not going to go all the way back. You saw the whole list of L2s. Generally, there's no built-in incentive to issue these fraud disputes, right? Like to say, or fraud proofs, right? To dispute something that's happened. With Polkadot, there really is, right? And it can be done automatically. And if one of these validators discovers that someone has been cheating, well, they get a reward, right? They're slashed and they get some of it, right? So, all right, great. So they all have, some incentive to actually follow this, right? So good economic incentives, right? Which is really nice. It's all sort of working without having to have people do any manual work. So some of this data is kept around. Some of it is not. So for the parachains, like the data on there, that's always going to be there. This is, again, very similar to optimistic rollups on Ethereum with dank sharding. Again, the time period is a little bit different. Excuse me, but similar idea here. That the L2 chains, they're going to keep their data, just like the parachains will keep their data. It's the sharded permanent record. The relay chain, there is a condensed permanent record, a receipt kept on chain of what happens. You can always look up and say, all right, well, this particular thing happened at this particular time, but it's just a condensed version of what's happened on the parachain. And our DA layer essentially stores all of these erasure-coded chunks for 24 hours. So there are quite a few benefits of this Polkadot approach. Sorry, it's a little bit small. So first off, we've got protocol level sharding, right? We can have the whole chain, all the different chains act not quite as the same chain, but sort of like the same chain. We have these, trustless interactions between them. Each shard has a relatively low barrier to entry. We don't have some of the limitations that you have, like with doing things with zero knowledge. Fast finality, so generally under a minute, in most cases under 20 seconds. I did not run numbers on that. I probably should have. That would have been a good statistic to have here. But generally, if there's no problems or not a lot of validators that have gone offline in the last in the last era or something, then generally 20 seconds or less. The data availability, the disputes, all of this stuff is built in. We don't need to L2s coming on. They don't need to have their own sequencers, right? Collators are much easier to spin up, and they can operate essentially trustlessly. But there are some drawbacks, right? So one of the things is that, remember I said that whenever you're interpreting code, or you have the guardrails essentially of a smart contract, it's not going to be as efficient if things were built directly into the runtime. And having something in the runtime, we've got a WebAssembly. We've got a WebAssembly that's also going to have, there's a little bit of overhead to that. But I think in actuality, this has not been a big issue. I don't think that has been the bottleneck at all for this. There's also a hard limit on the size and weights of these proof of validity blocks. So if you had some L2 that maybe had lots and lots of information, maybe you could use more space if you're willing to pay for it on Ethereum. You can't really do that right now. on Polkadot, once you are able to have multiple cores, of course, but I'm trying not to talk about things that will happen. I'm talking about things that are, exist right now. So again, benefits and drawbacks, but hopefully that gave you a good idea of what makes Polkadot different from all of these other solutions out there. All right? Thanks. I don't know if we have time for questions or something else happening right after.
Yeah, is there any questions on Bill's stuff? First, I will just say thank you so much, Bill. That was a really cool talk that I've never heard anyone go into such depth about comparing other L2s and other ecosystems, and I think it lacks a lot in the Polkadot ecosystem, where we're too often just in our tunnel vision about what we know and the terms that we know and stuff, and like there's so much stuff out there in other ecosystems that are just kind of equivalent. So I think it's important to gather that understanding. So yeah, round of applause again for Bill. Thank you so much.
Thank you.
We do have time for a question or two. Do you guys have like any specific thing you want to ask Bill?
Yeah.
Oh yeah, here's the mic.
So like I'm curious like how I had this question yesterday, but how solvable is consensus? Like if let's say if I was a parachain, if I was using a different consensus mechanism than the relay chain, then would there be a issue in interoperability there?
So parachains can't really have their own consensus, right? In general, right? So I'll talk about the exception, but in general, by coming into the Polkadot ecosystem, by saying, all right, here's what I'm going to do in order to produce blocks, here's my runtime, you're essentially like forcing yourself to use that basic Polkadot consensus mechanism. Now that said, you can have sub-consensus within this. So this is actually something I wrote an RFP for, because I'd be very curious to see someone implement it. And ALF0 did something similar, but they didn't do it exactly the way that I... So what you could have, for instance, is like every 6 seconds, okay, because that's going to be under asynchronous backing, the block time, that you would like sort of check in with the relay chain. But you may be producing blocks much more often than that, right? So you could have your own sub-consensus mechanism, like a Solana-style proof of history or something, but then like every 6 seconds have the second main consensus. So that's something that is possible. No one is doing it right now that I know of. But it's because what we're seeing is there are some chains that are using like a non-standard consensus mechanism like ALF0. And instead what they've decided to do is have essentially like a bridge parachain. So that parachain itself, right? So they're operating something with their own consensus mechanism over here. Then they have a Polkadot parachain whose job is just to bridge here and interact with Polkadot. So it's not involved in its consensus. But there's no reason you couldn't have the secondary sub-consensus.
Another question, yeah.
I have a question from the start of presentation. Pretty much, you said before that one dot is basically one vote, and for this vote, you're basically deciding also like what are gonna happen with Polkadot.
Yes.
After this, you said that in Polkadot, governance and staking is separate.
Correct.
So that's what I don't understand. Like you vote with dot, but you don't stake them.
So I see what you mean. So Polkadot is an account-based system, right? So let's say you have an account of 100 dot, right? So what's happening, behind the scenes, how I like to think of it is sort of like a glass of water, right? And you say, all right, I've got this much dot, 100 dot, okay, 0 to 100 dot, and you say I'm going to vote on this referendum, and with 50 dot, right? So a lock is put in place here, okay? So like you're at 50, halfway filled. And then you say, all right, now I'm going to vote on some other referendum, and I'm going to lock 50 dot. And that's, you can vote on multiple referenda, right? So you have another lock here. So you have 3, 4, 5. You can vote on however many referenda. I'll get to staking in a second, right? But the lock is not changing, right? It's always up to 50. And then I vote one time for 60. Well, now I've got this separate lock up at 60. So nomination and staking locks are very similar, right? And locks just mean you cannot transfer that dot away. Right? You're locking it for staking. You're locking it for what for governance. You can lock for all kinds of different things. So the locks are put at different levels. So let's say I stake with 25 dot. So I'm using the same dot for staking. That can be slashed. It can be taken away from me. But the lock is going to go to here on my account. So don't think of it as like, all right, when I'm staking, I'm like giving away that dot. It's like I'm voluntarily putting locks on my account, and these locks can overlap with each other. Or do you mean more philosophically?
No, I get it. So what if you staked your dot already, can you contribute with them as a governance?
Yes. So yeah, so again, so you've got your staking lock here. So I've locked 25, and then I have a governance 1, 2, 3, 4, 5, as many locks as I want. And those locks will eventually evaporate, essentially. You can unlock.
So is there even a reason not to not to lock your dot?
Well, yeah, but if it's locked, then you can't transfer it, right? So you may want to transfer it for all kinds of reasons, usually to send to an exchange, but maybe for for other reasons that you want to for instance participate in a crowd loan that requires giving your dot away, or in a nomination pool. So there are some reasons that you may not want to have this lock. But what the only thing the lock prevents you from doing is from transferring it. So you're right. If you have like 100 dot locked, it probably is not going to hurt you very much to vote, right? Because well, I don't care about having a lock on that 100 dot. It's already locked for staking. I don't really care about another lock. On the other hand, I would say people that are staking, accounts that are staking already are showing that they're like invested in the ecosystem. I'm not really worried about them also participating in governance.
Okay, thank you.
Yeah, thank you.